Today in class we played around a little bit with vectors, and as we're seeing, vectors aren't as simple as going forwards and backwards anymore. We're going to talk about vectors in two dimensions, which means any vector we have can exist in multiple dimensions. Okay, it's not just going to be right and left. And we have to remember that as we're adding our vectors together, we're always going to add those vectors tip to tail. We add our vectors one after the other. So what we did in class, just as a brief summary, is you had a bunch of vectors, you added them tip to tail, you followed what those vectors did and where those vectors took you. This would be vector 1 plus vector 2 plus vector 3 plus vector 4. How we would write that mathematically for these little displacement vectors, I guess. Yeah, we'll say x1, little vector sign on top of it, plus x2, little vector sign, plus x3, little vector sign, 3, plus x4, little vector sign. This, that's a half arrow. It's just an easy way to represent a vector. You don't always have to do that, but I'm going to do that some, and I want you to know what it looks like. Now, when we add these things together, x1 plus x2 plus x3 plus x4, they are going to equal what we call our resultant vector. The resultant is the sum of our vectors added together. Now, when we are adding vectors, we can't just say 3 plus 3 plus 2 plus 6. That's the length of each of these, 1, 2, 3. Because they're in different directions, we have to add them in a different way. Because our resultant vector goes from here to here. The resultant vector in this case is only that long. I don't quite know how long that is. So the way that we would add these things officially and analytically is to look at everything that's happening in the x direction and everything that's happening in the y direction. So vector 1 is all in the y direction. What we would say about vector 1, and this is how we wrote vector 1, vector 1 would be 3 units, so we'll say 3 meters to the north or up. Vector 2 is not in the y direction, it's in the x direction. So vector 2 would be 3 meters to the east. Vector 3 would be in the y direction, 2 meters south. South is in the opposite direction of north. So because that vector is 2 meters south, we're going to have to make it negative. And again, just like we did before, when we were going forwards or backwards, anytime we have something in the opposite direction, we need to make it negative. Now, for convenience sake, it's going to make sense to make south negative in cases like this. And then we have vector 4. Vector 4. And that's 6 meters to the west. Now the way that we're going to deal with these, since it's to the west, that's the opposite direction of east, we also have to make that negative. So when we're done with this, we need to find out in total what we did in the x and in total what we did in the y. So in the y direction, I have 3 meters north and 2 meters south. Well, if you go 3 meters north and then 2 meters south after that, your displacement in the y, and we're going to start changing things now, so things that happen in the y direction are going to be represented with y's, things that happen in the x direction are going to be represented with x's. Our resultant displacement in the y direction is 1 meter north. And our resultant displacement in the x direction is 3 meters to the west, and we can leave that as negative. Okay, that's what that negative means. So for our resultant, it's what we see right here, and then I'll draw it again. Resultant was 1 meter north, 1 meter north, and 3 meters west. So that describes both pieces of our resultant vector. That is our resultant vector. So we have labels for each of these. This part of the vector here is the component of my resultant vector that's in the y direction. We call it the y component. And then over here we have our x component. We're going to be using this language. I want you to be aware of it. Now that we have our vector, we need to do two things. One is to figure out the length of our resultant vector. Well, we know how to do that. A Greek man named Pythagoras helped us out with it. We used Pythagoras' theorem. So our resultant vector, we'll just call it r for convenience sake, our resultant vector is going to be the square root of 3 squared plus 1 squared. So our resultant vector is, what is that? The square root of 10. So the square root of 10 is, what do we got? 3.2 meters. So the length of our resultant vector is 3.2 meters, or the magnitude is 3.2 meters. That's one part. The second part of this is the angle, and we are going to discuss this a lot more on the next slide, but our angle, we need this angle right there. We want to know what direction that resultant vector is in. So to find that angle, we have to remember our sines and our cosines and our tangents. In this case, we're going to use the tangent. So the tangent of our unknown angle is the opposite side 3 meters divided by the adjacent side 1 meter. So in order to get the angle, theta is in your calculator arctan, or tan negative 1, that's the sine, of 3 over 1. You put that in, and the angle comes out to be 71.6 degrees. And we have to describe which way that is. So if we look at our vector, we started here straight north, and we swung out towards the west. So we're going to say west of north. Now, if you didn't quite catch that the first time, we're going to spend a little bit more time talking about directions and angles and things like that. But in order to tell me a resultant vector, you need to tell me these two pieces. Now, directions and trigonometry we're going to talk about really quickly. So let's talk directions. We're in 2 dimensions. Directions are important. In general, we have our basic compass. And it's got north, that's up, south, that's down, east, that's to the right, and west, that's to the left. But every now and again, well, not every now and again, a lot of the time, we're not going to have things that are straight up north and straight up south or straight east or west. We're going to have things that look like that. In this case, there are 2 ways we could talk about this vector. We could talk about this angle, we'll do that one in blue, and we could talk about this angle, we'll do that one in black. The angle in blue, we start off north and we move east. So the direction of that thing is east of north. And the direction of this other vector, the direction from the other way is north of east. When we're going to report the angle, we have to determine which way we moved in order to get that angle. They mean different things. And so if we go all the way around, I'll add these lines in red, kind of break it up. Any angle that's going to be in this direction, we moved south of east. We started east and we went south. So south of east. And then here we started south and we swung east. So we are east of south. I hope now you can start to see the pattern, but you may not, so we'll keep doing it. If we go here, we move west of south. We start south, we move west. That's west of south. And then here we're going to start west and swing down south of there. So that is, erase this, we don't need that, we don't need that, we don't need that, and we don't need that. So we're going to say here, we started west, we went south of west. And here we start west, swing north of west. And here we start north and swing west, that's west of north. That's going to be important when we're naming our angles for things. So, let's look at a basic triangle and all the math that we're going to have to do with our basic triangles. We're going to be nice and we're going to make sure that all of these are right triangles. Now, they may not be the special perfect right triangles. Now, just as a note, what I am showing here is that this vector is being added to this vector, giving me this resultant vector. But for the purpose of now, we're not going to call that the resultant. I know that these two are being added together because they are tip to tail. And I know that this is the resultant because it starts where I start and it ends where I end when I added the other two together. Now, for a little right angle geometry stuff, tons of fun. I know you love it. This is our hypotenuse, this is our opposite side, and this is our adjacent side. And they're called that because this side is opposite to my angle, this side is adjacent to my angle, and the hypotenuse is the long side. Adjacent means touching. So, we have set ratios for angles in 90-degree triangles, and we get those by our trigonometric functions sine, cosine, and tangent. So sine of the angle that I have written down is the ratio of the opposite side to the hypotenuse. Cosine of the angle I have written down is the ratio of the adjacent side to the hypotenuse. And then the tangent of that angle is the ratio of the opposite side to the adjacent side. Another way to write tangent as well is the sine over the cosine. We may or may not need that as time goes on. It is good to know. So, for any angle that you can think of in degrees, the sine of that angle, the cosine of that angle, and the tangent of that angle are all stored in your calculator. So if you hit sine 30, it's going to give you 1/2. What that means is that the opposite side of a 30-degree angle is always 1/2 the length of the hypotenuse. Always. That's what sine 30 means. This is going to help us determine angles when we're adding things together. Now, you are not always going to have vectors that are convenient. Sometimes you might have something that is, let's say, 10 meters at 30 degrees north of east. You're going to need to know what to do with that. Now, if you're graphing it, you'll have to be exact and you'll have to use a protractor. But we're not really graphing anymore. We're moving on to the analytical methods. So, you're going to need to sketch out what that vector might look like. So, 10 meters at 30 degrees north of east. Well, if this is north and this is east, it means that my vector is going to start east and swing up north. So, that vector is going to point in this direction. So I'm going to have 10 meters this way, and that angle is 30 degrees. Now, if I'm adding a lot of these together, I'm going to need to break up or resolve the vector into its components. What that means is that I'm going to take the vector and break it into its components. So resolving is breaking into its x and y components. So looking at this vector, its x component is here, and its y component is here. For this thing, we know the hypotenuse and the angle. What we're looking for is the x, which in this case is the adjacent side, and the y, which is the opposite side. So, if I'm talking about the adjacent side, I'm talking about cosine. So cosine of 30 is equal to adjacent x over hypotenuse 10. So I want to solve this whole thing for x. I multiply both sides by 10, and I get 10 cosine 30 equals the x component here. So that x component comes out to be, what is that? 8.66 meters. So my x component is 8.66 meters, and since that's pointing to the east, it's going to be positive. For the y component, we're talking about the opposite side, so we're talking about the sine of 30 degrees. The sine of 30 degrees is going to be the opposite y over the hypotenuse 10. It's the same idea behind the math. We're going to multiply both sides by 10. So 10 times sine of 30 is equal to my y component. When you do that out in your calculator, 10 sine 30 comes out to be 5 meters, and if we look at that little piece, it's pointing up 5 meters north. We're going to make it positive 5. So when you have a list of vectors that is a little complicated, like the one we just broke down, you're going to have to break each vector down into its x and y components, and then add them together like we did before.